Welcome. This is the Kansas State University presentation for the ASHRAE HVAC system selection as part of the 2014 Student Design Competition. The progression of this presentation has been laid out in the order of Introduction, Project Goals, System Options, How the System Works, System Components, Pros and Cons, Innovation, Integration, Economics, and Recommendation. Next, we will introduce the project. The members of the design team include John Gato, Katie Helmer, Lexi Oliver, Alex Pent, Megan Wakowiak, and Gordon Zimmerman. The design team's advisors are Julia Keene and Fred Hassler. The proposed building is a two-story, 31,000 square foot renovation located in New York City. The building will be remodeled and used as the headquarters, office, and research facility for portable refrigeration devices. Due to the diversity of uses, we have divided the building into 4 occupancy categories to explain the needs of each space. The 4 categories are office and administration, research and development, clean room, and server room. The building loads were calculated in Train Tray 700, and the percentages and reasons for the load in each category are as follows. The office space makes up 46% of the cooling load and 54% of the heating load. This is due to envelope loads and the size of the space. Next, the research and development space makes up 36% of the cooling load and 44% of the heating load, which is a result of the large amount of outside air needed due to high exhaust rates. Then the server room makes up 17% of the cooling load and will never require heating. This is a result of the heat gain from the data equipment. And finally, the clean room makes up only 1% of the cooling load and 2% of the heating load because it is a small space with little heat gain in an interior zone of the building. Before selecting an HVAC system for this project, the following goals were considered. Low life cycle cost. This takes into account first cost and operational cost over a 50-year life. Comfort and health. This focuses on maintaining a high indoor environmental quality for the occupants. Low environmental impact. This tries to minimize water consumption, carbon footprint, and total use of refrigerant. Creative, high-performance green design. This incorporates creative ways to efficiently and comfortably condition the space. And synergy with architecture. This considers the effect the HVAC system will have on the aesthetics of the building and the spatial requirements needed for various systems. After considering the goals for the project, the following systems were analyzed in detail: variable refrigerant flow, ground source heat pumps, and active chilled beams. To evaluate the 3 systems, a decision matrix was formed and points were given to each system based on the project goals, owner requirements, and building design parameters. After this comparison, the ground source heat pump system was selected as the HVAC system for this building. Next, we will discuss how the system works. Ground source heat pumps work by pumping water through bores in the ground, which act as a heat source or a heat sink. To take the water to the terminal units, redundant pumps with a variable frequency drive are used. The water is then routed to water source heat pumps connected in parallel, which inherently allows load to be shared between the heat pumps. This section will begin by describing the ground source heat pump components that apply to the entire system. Then we will move into discussing components that apply specifically to an occupancy category. Component 1 is the boreholes. Boreholes are composed of piping which uses the ground as a heat sink or heat source depending upon the outside temperature. To maximize heat transfer in the boreholes, a twister borehole technology will be used. A standard ground source borehole requires 3 pipes, 2 that are connected in a U-bend to allow water to flow between them, and 1 that is left open at the bottom to grout the space between the piping and the earth. The twister borehole uses the same area as one traditional borehole, but wraps 8 3/4-inch pipes around a 2-inch center core to create 4 loops. This installation method creates a more even distribution of grout and has greater internal separation, exterior pipe surface exposure, and utilization of borehole surface area. The twister borehole technology provides more heat transfer capacity compared to a traditional borehole, which allows for fewer and more shallow boreholes, which will lower construction costs. The bore field will be sized based on the total cooling load, so no other central mechanical cooling or heating equipment is necessary. Component 2 is the pumps. To transfer the water from the boreholes to the space, 2 variable frequency drive pumps set up in parallel are used. The 2 pumps in parallel allow for redundancy if a pump were to go down. The variable frequency drive allows the pump speed to change based on the load to save energy. Component 3 is the heat pumps. The heat pumps will be ducted units located at the zone level that utilizes a refrigeration cycle to transfer heat between the water loop and the space. The refrigeration cycle can be reversed based on the needs of the space it is serving to allow for simultaneous heating and cooling. Component 4 is a dedicated outside air system, or DOAS, which will supply the building with makeup air. The DOAS for the building will be a heat pump with electric preheat to ensure the minimum entering air temperature recommended by the manufacturer. The DOAS will also utilize a desiccant heat exchanger located on the roof to recover heat from the exhausted air. In the summer, outside air will enter the conditioner. The sensible and latent heat will be removed from the air, and then the air will be supplied to the space. Next, the heat will be transferred by a heat exchanger to the return air in the regenerator. After the return air absorbs the heat, it will be exhausted. In the winter, the cycle is reversed so the supply air absorbs the heat that is transferred from the exhaust air stream. As part of the system component section, we will now discuss the components within each occupancy category. A biowall is utilized in the office and administration areas that make up occupancy category 1. This is a wall of vegetation created by attaching plants to a mesh grid. Return air will be pulled through the plant wall by the use of fans. When the air goes through the wall, the plants will capture excess carbon dioxide and 80 to 90% of volatile organic compounds, which meet ASHRAE Standard 62.1 2010 Table B1 to allow ventilation to be reduced to what is needed for building pressurization. After going through the wall, the clean air will be returned to the heat pumps and be distributed to the spaces. The benefits of the biowall include a reduction of ventilation in the office spaces that will significantly reduce the energy consumption due to conditioning less outside air, while providing an architecturally pleasing component that contributes to the indoor environmental quality of the space. The biowalls will be located around the office and administration areas as shown in green on the floor plans. A special lab equipment system will be used in the research and development areas to make up occupancy category 2. The owner's requirements for lab equipment within this space resulted in a high quantity of exhaust. Therefore, a sophisticated system is needed to regulate the varying exhaust. Venturi valves will be used to effectively regulate room supply, room exhaust, and hood exhaust rates. A laboratory controller will connect the Venturi valves with a thermostat, room pressure sensor, and fume hood controllers to maintain the required room pressure and exhaust. Next, we will discuss the components within the clean room that makes up occupancy category 3. The required ventilation for the clean room will be taken from the adjacent research and development space through grills located near the floor at one end of the clean room. The incoming air will mix with the clean room return air and pass through a fan-filtered box which houses the required filters. Once filtered, it is introduced into the clean room at the ceiling, which will direct the air in a unidirectional flow. The air will then flow through grates in the floor, and the required amount of air will be returned to the adjacent R&D space. To serve the internal loads in the space, a heat pump is located within the fan-filtered boxes. Now we will discuss the components of the server room, which makes up occupancy category 4. To condition the load due to the server racks, a water wheel will be used as the primary method for cooling, and a water-to-water heat pump will be used for any additional cooling needed. The water wheel is used to reject heat from the water loop, which cools the server racks throughout the year. In the summer, rainwater will be collected from the building roof drain system. The captured rainwater will be poured over a water wheel, causing the wheel to turn and the water to reject heat through evaporative cooling. The small amount of power generated from the turning of the wheel will assist in powering the pump. Next, the water will drop into a basin below and be piped to a heat exchanger. In the interior loop, water will flow through water-cooled server racks, absorbing heat and sending it back to the heat exchanger. The heat will be transferred to the exterior loop and the process will repeat. If the water wheel is unable to cool the water to the correct temperature, the water-to-water heat pump will assist in the cooling process. If the water supply is depleted, the water-to-water heat pump will provide all necessary cooling. This unit will be placed underneath the raised floor in the server room and cannot be seen in the figure. The water basin will act as a waterside economizer when outside conditions are optimum. When the outside temperature drops below 40 degrees Fahrenheit, the water basin will be heated to prevent freezing. After defining the system components, we can now discuss the pros and cons of the ground source heat pump system we have outlined. The advantages of the ground source heat pump system include low operating cost due to the ability to share loads between spaces and transfer heat to and from the ground. High familiarity due to the frequent use of heat pumps. High durability due to the life and predicted maintenance for the heat pumps. Also, the bores have a life of 50 years and will not need maintenance. Redundancy due to the large number of boreholes. Adaptability due to the ease of installing and moving heat pumps. No facade integration is necessary due to no visible equipment, which provides architectural synergy. Low water use due to a closed system and utilization of rainwater storage. Small carbon footprint due to the energy efficiency of the system. Decreased ventilation due to the biowall filtering the return air. And finally, energy efficient cooling capability for the server racks due to the water wheel. The disadvantages of the ground source heat pump system include higher first cost, difficult installation, and space for the bore field is required. The innovative components of the ground source heat pump system are the twister borehole technology used to increase heat transfer capacity, the biowalls used to decrease ventilation and increase indoor environmental quality, and the water wheel used as a low-cost way to reject heat to the atmosphere. An ideal system should integrate well with the architecture, occupants, and environment. Architectural integration is achieved by the ground source heat pump system by integrating well with the exterior facade and the occupied spaces, and by decreasing the required space needed in the mechanical room. The ground source heat pump system integrates with the occupants by providing a healthy and safe environment, allowing for maximum comfort, and providing optimum sound levels. To integrate well with the environment, the ground source heat pump system decreases water use and carbon footprint and complies with ASHRAE Standard 15 for refrigerant use. A 50-year life cycle cost analysis was performed to analyze the first cost and operating cost of the three systems. First cost was calculated by comparing the differences between the systems. Variable refrigerant flow had the lowest first cost. The active chilled beam system was 13% higher, and the ground source heat pump system was 31% higher. The operating cost calculated the present-day value of the utility, maintenance, and repair costs. Ground source heat pump had the lowest operating cost. The variable refrigerant flow system was 27% higher, and the active chilled beam system was 34% higher. Even with the high first cost, ground source heat pump had the lowest life cycle cost. Using the previously discussed sections, the following can be concluded. The system components work together to make the system the best option for this project. The pros and cons list shows that the positives outweigh the negatives for the ground source heat pump system. The innovative components for the system create a unique way for a more sustainable design. The integrated components display that the ground source heat pump can satisfy all the needs of the building. And the economics of the three systems show that the ground source heat pump system has the lowest life cycle cost for the three options. After reviewing the previous sections, the Kansas State University design team recommends a ground source heat pump system for the Portable Refrigeration Device Research and Manufacturing Center. This will provide the owner with a system that meets all of the requirements. Thank you for listening. This has been the Kansas State University ASHRAE Student Design Team.